Hey everyone, in this video I'm going to talk about how to select electrical components, specifically resistors. So first off, what is a resistor? It's a device that has a well-defined relation between voltage and current. It's described by Ohm's law, that is V equals IR. So the current through the resistor is proportional to the voltage across the resistor, and that constant of proportionality is R, the resistance. There's a lot of different ways to build a resistor. Fundamentally, you need a device that kind of conducts electricity. It's not a really good conductor, it's not a really good insulator, it's somewhere in between. And that somewhere in between tends to stay stable. That somewhere in between is, of course, the resistance. The first one I'll talk about is thick film resistors. These you want to consider your everyday normal resistor. These are going to be really cheap. We're talking less than pennies for most of them. The way these are built is you start with a ceramic substrate and then you put a conductive ceramic layer on top of that. That is the thick film, and you fire it. Thick film, it's cheap, it's common. Consider this your default choice for most applications. Next one is going to be thin film. This one you also start with a ceramic substrate, but instead of putting a paste layer on top of it, you actually sputter a thin film. That's where the name comes from. You sputter a thin film of conductive metal onto that substrate. And then usually you'll trim it with lasers to really dial in the value of the resistor. Now here's one that's actually obsolete, carbon composition or carbon comp. These, if you can still find them, have excellent pulse rating capability, but horrible precision. You might see as much as a 20% tolerance on the resistance value. I just mentioned those for completeness. As of a couple of years ago, really everyone stopped making them, so you can't buy them anymore unless you're buying new old stock. And for most designs, you're going to want to use stuff that is actively being produced. Another type is metal element resistors. This is literally just a piece of metal that's cut down into the shape of a resistor. These are good for low value resistors, so we're talking about shunts for current sensing. They tend to have really good power dissipation because they're made of metal, and they tend to be pretty stable over temperature as well. So if you need a low value resistor, consider a metal element. Now a similar kind of resistor to the metal element is a metal foil resistor. This is where you start with a ceramic substrate and you put a foil on top of it. Then you cut back that foil with lasers to dial in the exact resistance that you want. Last one I'll mention is wire wound resistors. It used to be that you could find these for small axial through-hole resistors. I'm not sure they're so popular anymore. They tend to have a very large equivalent series inductance because it's a coil of wire. So for your small everyday resistors, you generally don't want to use wire wound. The place that you will find these, that they're extremely useful, is for high power resistors. So we're talking hundreds of watts or even thousands of watts of power dissipation capability. Big resistors like that, sometimes you call them corn cob resistors because they look kind of like a corn cob. Now there are other ways to build resistors. This is not a comprehensive list, this is just the most common ones that you might run into, or at least the ones that I think about. Next we're going to talk about the packages that you might find resistors in. I would say the most common or the most ubiquitous type of package is the surface mount package. So this is a chip resistor. You can find these all the way down from 0201, like a grain of sand, all the way up to, say, 2512 at the bigger end. Now, another way to package resistors is through-hole, and most commonly this will be through-hole axial. The most common size and shape of these is going to be the quarter-watt resistor. It's going to have a lead spacing of roughly a ½ an inch, so they actually take up quite a bit of space on your board. The package size is specified directly as a power rating, so you have the 1/8 watt resistor, you have the quarter-watt resistor, you have the ½ watt resistor, and so on, with more power dissipation resulting in a bigger package. And the packaging for very large resistors, you call these chassis mount. That just means that you got to grab onto it with some kind of bracket and hold it where it's safe. So with the types and the packaging out of the way, let's talk about the specific parameters you care about when you're choosing a resistor. And with these, there's really about 4 things that you care about. The first one is, of course, the value of the resistor that's specified in ohms. That's the linear slope between the voltage and the current. Next one is the resistance tolerance. So let's say you go out and you buy a 1 kilo ohm resistor and you measure it. It's probably not going to measure exactly 1 kilo ohm. It's going to measure 1 kilo ohm within some tolerance. So that tolerance is specified usually as a percentage plus or minus. So that 1 kilo ohm plus or minus 1%, for example, that means that you can get plus minus 10 ohms. So you could measure 1010 ohms and the resistor is in tolerance. You could also measure 990 ohms and the resistor is in tolerance. It used to be that 5% and 10% resistors were really common, especially in the 1970s, 1960s, but the cost of precision has gone way down. So if you know that you don't need precision, you can still go with the 5%, save a little bit of money. But resistors are cheap and precision is cheap, so you can get 1% and still not pay that much for your resistor. Now there's a tolerance on the resistance, and that's just a fixed value, but what about things that change with temperature? The value of your resistor will change with temperature, and usually that's going to be between 5 and 1,000 parts per million per degree Celsius. So every degree Celsius that you move this resistor away from room temperature, or usually 25 C, the resistance value is going to go up or down. Most resistors are designed to be very stable, with thin film being the most stable of all, and carbon comp being extremely unstable. You can also actually have thermistors, which are designed to have a very large coefficient of thermal resistance. That is, as you change the temperature, the resistance changes a lot. This can be useful for measuring temperature. Thermistors are used all the time. Now, if you don't need an extremely precise resistor, don't pay for one. You're going to pay a lot more for a resistor that is precise down to 5 parts per million. A lot of the times you just don't need it. Last key parameter to talk about is the power handling, or the power dissipation capability. The general rule is the bigger the package, the more power it can dissipate. So what I consider my default choice for a resistor is an 0805 surface mount package. That is nominally rated for 1/8 of a watt or 125 milliwatts. If you need more power handling capability, you just pick a bigger package. So for example, the 1210, which is a bigger surface mount package, is rated for a 1/2 watt or 500 milliwatts, which is quite a lot. So what's the big takeaway? Picking a resistor doesn't have to be so hard. There are different types of resistors. There's a few parameters that you need to know, but for the most part, you can go with a thick film resistor, and that's going to be just okay for most applications. Before I go, of course, I need to discuss how do you actually calculate the power dissipation in your resistor? Well, it's not that hard. What you need is the equation for power, and then you plug in Ohm's law, and you can either get P equals V squared divided by R, or P equals I squared R. Those are equivalent. It just depends how you want to describe the operating point of your resistor. So let's say you have a 1 kilo ohm resistor and you're putting 5 volts across it. The power dissipation is going to be V squared divided by R, or this, 25 milliwatts. Just because you're dissipating 25 milliwatts, now does that mean you need to go with a really small package? No. You can go with a larger package and dissipate less heat in that package. It's safe if you do that. If you go the other way, if you dissipate too much power, that's when you're going to start cooking your resistors. In my designs, when I'm choosing, say, a default size of resistor, usually I go for the 0805. And the simple reason is it's big enough that it's still easy to solder by hand. 603, 402, those get a little bit more tricky. And that's about it. That's most of what you need to know when you're picking a resistor. I hope you found this video interesting. I hope it's educational. My name is Colby. I'm a power supply designer. I hope you enjoyed this video. Thanks a lot. Bye-bye.